All right, today we're doing a technical overview of the Google Gemini/Gemini CLI repository. We'll be looking at its architecture, its core functions, and the automation that keeps it all running smoothly.
So here's how we'll break it down. We'll start with the core purpose and architecture. Then we'll dive into the CLI application itself, followed by a look at the AI agent orchestration. After that, we'll cover authentication, external integrations, and we'll finish up with development and automation.
Okay, let's get started with Section 1, the core purpose and architecture of the repository.
At its heart, the repository's main job is to give developers a command-line interface to work with the Google Gemini AI model. It's really built for tasks you'd encounter in the development lifecycle, things like analyzing code, generating new code, and automating various processes.
The architecture is designed to be a modular command-line app. The CLI entry point is right at the center, and it's what orchestrates everything else. It directs the AI agent orchestration module for all the LLM interactions. It handles secure access through the authentication module, and it coordinates with core services to talk to external APIs and IDEs.
Moving on to Section 2. Here, we'll take a look at the main application logic, which is spread across the repository's various packages.
The code base is neatly organized into distinct packages, which creates a really clear separation of concerns. The /packages/CLI directory is the main entry point, using TypeScript and yargs to process commands. All the foundational logic for LLM interaction is in /packages/core. Then you have other packages for specific things, like the experimental A2A server, the VS Code extension, and all the automation scripts. The application actually supports two main ways of running. First, there's the interactive UI, which is built with Inc and React. It gives you a dynamic terminal experience for when you're using it directly. Then there's the non-interactive CLI mode. This one is really designed for scripting and automation. It just processes commands in sequence and can output structured formats like JSON without needing any user input.
All right, Section 3. This is where we go beyond just simple commands and look at how the system defines, manages, and executes AI agents to handle more complex tasks with large language models.
So what do we mean by an AI agent in this system? Well, it's a formal entity that's configured with a very specific purpose. It has a connection to an LLM, a set of tools it can use, and a defined lifecycle that guides it from the start of a task to the finish.
The agent lifecycle itself follows 4 distinct stages. It all starts with a formal agent definition. That definition then gets discovered and loaded by the agent registry. From there, the agent executor takes over to manage the back-and-forth conversation with the LLM. And finally, the agent signals that it's done by calling a specific task complete tool, which includes its final structured output.
Now, there are several key classes that make all this orchestration happen. The agent executor is the one that controls the interaction flow. The agent registry basically acts as a service locator for all the agent definitions. You also have the sub-agent tool wrapper, which lets one agent call another agent as if it were a tool. This is really useful for breaking down complex tasks. And then the Gemini client handles the direct communication with the model itself.
To optimize for performance and cost, this system uses dynamic model routing. This is a layered set of strategies that get applied in a specific order. First, it checks if a user has explicitly overwritten the model choice. If not, a classifier strategy might use a smaller, faster LLM just to figure out how complex the task is and then route it to the right model. For resilience, there's a fallback strategy that can switch to a more stable model if errors pop up, and of course, there's always a default model ready to go.
Let's move on to Section 4, where we'll cover the system's approach to secure authentication and how it manages configuration. The CLI actually supports 2 main authentication flows. For Google services, it just uses the standard OAuth 2.0 flows, including application default credentials. For other platforms, it uses a generic flow based on the Model Context Protocol. This implements the authorization code flow with PKCE for an extra layer of security.
Secure token storage is managed with a very clear hierarchy. The system always tries to use the most secure method available. First, it attempts to use the native OS keychain through the keytar library. If that's not available, it falls back to a securely encrypted file. It also has a built-in migration path to upgrade credentials from any older, unencrypted storage that might exist. The central config class is really the single source of truth for managing everything at runtime. This class is responsible for initializing core services like the Gemini client, it handles authentication events, it enforces security policies like approval modes, and it also manages those model selection strategies we just talked about.
This next section is all about how the CLI communicates with external systems. This is pretty essential for providing context-aware AI help, and it includes things like the A2A server and direct IDE integrations.
A really key component for integration is the experimental application-to-application server, or A2A server. It provides a dedicated HTTP interface that allows external applications, like an IDE, to set up a persistent, interactive communication channel with the Gemini agent while it's running.
Communication with this A2A server follows a well-defined sequence. A client kicks things off by sending a post request to create a task. The server then acknowledges this by assigning a unique task ID and sending it back. After that, the server uses server-sent events, which is a technology for pushing real-time data, to stream status updates back to the client, giving it a continuous look into what the agent is doing. The VS Code integration provides even deeper, more context-aware features. The ID server component sets up secure local communication. The Open Files Manager keeps track of what the developer is focused on, like which files are open and what text is selected to provide relevant context. And the Diff Manager integrates directly with the ID's native UI to show proposed code changes.
In our final section, we'll cover the scripts and workflows that support the repository's development lifecycle. These are what ensure code quality and automate the release processes. The repository has a pretty comprehensive suite of automation scripts, all organized by function. You've got scripts for building the application and its sandbox environments, for enforcing code quality with linting and pre-commit hooks, for managing versioning and packaging for releases, and for making the local development experience much smoother.
The management of third-party executables, like the rip-grip search tool, is a great example of this automation. The system first identifies the right binary for the user's OS and architecture. It then retrieves it, but it also caches the download so it doesn't have to do it again. The executable gets extracted, and its path is dynamically resolved so that other modules can use it without any extra work.
So to sum it all up, the Gemini CLI repository is a highly structured and extensible framework. Its modular architecture, the sophisticated AI agent orchestration, and the robust automation really provide a solid foundation for anyone looking to build powerful AI-driven developer tools that run right from the command line.